Implementation of SpaceX's recovery protocols in 2024, a comprehensive report. Overview. In 2024, SpaceX is set to enhance its astronaut recovery protocols with an investment of $3 million aimed at significantly improving safety measures during recovery operations. This initiative is divided into 4 structured phases, each designed to systematically address and enhance the astronaut recovery process. The commitment to astronaut safety is a testament to SpaceX's ongoing efforts to lead in space exploration and technology. Detailed breakdown of the phases. 1. Assessment phase. The first phase focuses on a thorough evaluation of existing recovery operations and safety incidents. This involves data analysis. SpaceX will analyze historical data from past missions, including incident reports and astronaut feedback. The goal is to identify patterns and weaknesses in current protocols. Incident review. A comprehensive review of previous recovery incidents will be conducted to understand the causes and effects of any safety breaches. This includes examining both successful recoveries and those that encountered difficulties. Stakeholder engagement. Input from astronauts' recovery teams and safety experts will be solicited to ensure a holistic view of the current challenges. This phase is crucial as it sets the foundation for all subsequent improvements, ensuring that decisions are informed by empirical evidence and actual experiences. 2. Development phase. Following the assessment, SpaceX will enter the development phase, where new technologies and recovery procedures will be formulated. Key activities include innovative technology design. Engineering teams will work on developing advanced safety gear and recovery systems. This may include enhanced personal protective equipment (PPE) and automated recovery systems that can operate in a variety of emergency scenarios. Collaboration with experts. SpaceX is expected to collaborate with aerospace safety experts, engineers, and possibly academic institutions to leverage the latest research and innovations in safety technology. Procedure formulation. New operational protocols will be drafted focusing on risk mitigation and response strategies for various recovery scenarios. This phase emphasizes proactive development to address identified weaknesses, ensuring that the new protocols are cutting-edge and effective. 3. Testing phase. The third phase involves rigorous testing of the newly developed technologies and procedures. This phase includes simulations. Extensive simulations will be conducted to mimic a range of emergency situations that astronauts may encounter. These simulations will help refine protocols and ensure that all team members understand their roles in a crisis. Live testing. In addition to simulations, live tests will be performed to validate the effectiveness of new technologies and recovery processes. This may involve controlled environments mimicking real recovery scenarios. Data collection. Metrics will be gathered during testing to assess the performance of new systems. This data will be essential for making necessary adjustments before the full-scale implementation. The emphasis on testing ensures that any newly developed technology is not only theoretically sound but practically viable in real-world situations. 4. Implementation phase. The final phase is the rollout of the new recovery protocols across SpaceX's astronaut missions. This includes training programs. Comprehensive training sessions for astronauts and recovery teams will be initiated to familiarize them with the new protocols and technologies. Emphasis will be placed on hands-on training and scenario-based learning. Field integration. The new recovery protocols will be integrated into upcoming missions, allowing for real-time application and feedback collection. Continuous monitoring. Post-implementation, SpaceX will monitor the effectiveness of the new protocols, closely collecting data and feedback to refine processes further. This phase is critical as it ensures that the new measures are effectively incorporated into the operational framework of SpaceX missions. Budget allocation. The total budget of $3 million is strategically allocated across the 4 phases to ensure a comprehensive approach to astronaut safety. Assessment phase, $500,000 for data collection analyses and stakeholder engagement. Development phase, $1.2 million for technology development and expert collaborations. Testing phase, $800,000 dedicated to conducting simulations and live tests. Implementation phase, $500,000 for training programs and initial field integration. This budget reflects SpaceX's prioritization of safety and its commitment to investing in long-term solutions for the challenges of space travel. Common themes and key points. Data-driven improvements. A recurring theme across all phases is the emphasis on learning from historical data to inform future protocols. The commitment to using empirical evidence to guide decisions is evident throughout the process. Rigorous testing. The importance of thorough testing cannot be overstated. Each phase reinforces the need for validation through simulations and life scenarios to ensure that new technologies and procedures are effective under real-world conditions. Phased approach. The structured phased implementation strategy is designed to minimize risks while enhancing safety measures incrementally. This methodical approach allows for adjustments at each stage based on feedback and performance. Differences in perspectives. While various sources highlight different aspects of the recovery protocols, they all converge on the importance of comprehensive testing and historical data analysis. Some sources may focus more on the technological innovations being introduced while others emphasize the training methodologies that will be employed. Additionally, discussions around potential public-private partnerships may vary, with some sources considering these collaborations as essential to enhancing astronaut safety while others place less emphasis on this aspect. Timeline of events. Q1 2024. The assessment phase commences with data collection and analysis of past recovery incidents, setting the stage for subsequent improvements. Q2 2024. The development phase begins, focusing on the creation of new technologies and recovery procedures based on the assessment findings. Q3 2024. Testing of new protocols starts, involving both simulations and live tests to ensure reliability and effectiveness. Q4 2024. The implementation phase rolls out, featuring comprehensive training for astronauts and recovery teams, marking the full integration of the new recovery protocols. Conclusion. SpaceX's commitment to enhancing astronaut safety through a structured, phased approach and a significant budget allocation demonstrates a proactive stance toward addressing safety challenges in space travel. By focusing on data analysis, technological advancement, and rigorous testing, SpaceX positions itself as a leader in astronaut safety protocols. As the 2024 implementation unfolds, the outcomes of these efforts will likely set new standards for safety in the aerospace industry, paving the way for future advancements in human spaceflight. The content provided outlines SpaceX's recovery protocols for astronaut safety in 2024, detailing a structured implementation plan comprising 4 phases with a budget of $3 million. Here are some counterintuitive pieces of information derived from the text. 1. Budget allocation versus perceived costs. At first glance, one might assume that enhancing astronaut safety, especially in the high-stakes environment of space travel, would require a significantly larger budget. However, SpaceX's allocation of $3 million may appear modest compared to the potential costs of astronaut training and mission failures. This suggests that SpaceX has found ways to implement safety protocols efficiently, leveraging existing technologies and innovations rather than overextending financial resources. 2. Focus on historical data. It may seem counterintuitive that the initial phase of this safety improvement plan centers heavily on reviewing past incidents and feedback rather than immediately innovating new technologies. However, the emphasis on learning from historical data indicates a strategic approach where understanding previous failures is considered more critical than rushing into new developments without a solid foundation. 3. Phased approach. The structured four-phase implementation may seem overly cautious or bureaucratic for a tech-driven company like SpaceX, which is known for its rapid iteration and agile methodologies. However, this methodical approach underscores the importance of thorough testing and validation. It suggests that even in a fast-paced industry, taking the time to ensure that protocols are effective can ultimately save time and resources in the long run. 4. Collaboration with experts. While it is common in industries to rely on internal teams for innovation, SpaceX's decision to collaborate with external aerospace safety experts may seem surprising. This could imply a recognition that internal resources alone may not suffice for the complex challenges of astronaut recovery, highlighting a humility and openness to external insights that is not always found in leading tech companies. 5. Continuous monitoring post-implementation. The idea that protocols will be continuously monitored and refined even after implementation could challenge the notion that once protocols are in place, they are set in stone. This dynamic approach promotes adaptability and responsiveness, suggesting that astronaut safety is not a one-time effort but an ongoing commitment to improvement. 6. Training is a core component. While one might expect that the focus would primarily be on technology and equipment, the significant emphasis on training for astronauts and recovery teams underscores the understanding that human factors are critical in safety protocols. This suggests a holistic view of safety that encompasses both technological and human elements, which may not be the primary focus in other high-tech industries. These counterintuitive insights reveal a deeper layer of thought and strategy behind SpaceX's recovery protocols, indicating a commitment to astronaut safety that balances innovation with methodical assessment and continuous improvement. In analyzing SpaceX's implementation of enhanced recovery protocols for astronaut safety in 2024, several important aspects of the report may be easily overlooked by the general public. Here's a breakdown of these critical elements and their significance. 1. Data-driven improvement focus. The assessment phase emphasizes a thorough review of past recovery operations and safety incidents. While many may recognize the importance of learning from past mistakes, the depth of analysis planned is significant. SpaceX's commitment to understanding specific failures and the nuances of astronaut feedback reflects a willingness to engage in self-criticism and continuous improvement. Significance. This data-driven approach is crucial for developing effective safety measures. It indicates that SpaceX is not merely interested in surface-level improvements but is prepared to delve into complex issues that have previously impacted astronaut safety. This can lead to more tailored solutions that are directly informed by real-world experiences, ultimately enhancing the effectiveness of recovery protocols. 2. Collaboration with experts. The development phase involves collaboration with aerospace safety experts and engineers. While the mention of technological innovations might capture attention, the significance of these partnerships is often understated. Significance. Engaging with specialists can lead to breakthroughs that internal teams may not achieve alone. This collaborative effort can result in the development of cutting-edge technologies and procedures that leverage diverse expertise, enhancing the robustness of safety protocols. Moreover, it reflects an industry-wide acknowledgement that safety is a shared responsibility which can foster innovation across the sector. 3. Rigorous testing protocols. The testing phase is highlighted as critical for validating new recovery technologies and procedures. However, the extent and rigor of testing, specifically simulations and live tests under various scenarios, are often glossed over. Significance. Comprehensive testing is not just about ensuring that new technologies work, it's about understanding their limits in real-world situations. The ability to simulate extreme conditions can help prepare astronauts for unexpected scenarios, which is vital for mission success. Furthermore, the iterative nature of testing allows for continuous refinement, ensuring that protocols evolve based on empirical evidence rather than assumptions. 4. Phased implementation strategy. The structured phased approach to implementation might seem like a typical project management strategy, but its significance lies in risk management and adaptive learning. Significance: by breaking down the implementation into phases, SpaceX mitigates the risk of a complete failure of new protocols. Each phase allows for assessments, adjustments, and enhancements before moving forward. This adaptability is crucial in the high-stakes environment of space travel, where the implications of safety failures can be catastrophic. It also fosters a culture of learning and improvement where feedback is continuously integrated into the process. 5. Budget allocation and resource commitment. The allocation of a $3 million budget across the 4 phases may seem like a straightforward financial commitment, yet the strategic distribution of these funds is noteworthy. Significance: this budget reflects SpaceX's prioritization of astronaut safety over other potential investments. The deliberate allocation to various phases indicates a comprehensive approach to funding that takes into account the different needs at each stage, from research and development to training and implementation. It underscores the message that safety is a foundational aspect of their operations, not merely an afterthought or a regulatory requirement. 6. Continuous monitoring and feedback mechanisms. The plan for continuous monitoring and feedback during the implementation phase is a critical element that might not receive full attention. Significance: this aspect ensures that the recovery protocols remain relevant and effective even after their initial rollout. The dynamic nature of space missions means that conditions can change rapidly, and having a system in place for ongoing evaluation can help SpaceX adapt its protocols to new challenges. This proactive stance towards safety management is essential for maintaining high standards in astronaut care and operational integrity. 7. Potential for public-private partnerships. The mention of public-private partnerships in enhancing astronaut safety, though less emphasized, holds significant implications for the future of space travel. Significance: such partnerships can lead to shared resources, expertise, and innovations that benefit both parties. The collaboration between government agencies and private entities like SpaceX can foster a more comprehensive approach to safety that leverages the strengths of both sectors. This could lead to advancements in technology and procedures that may not be possible through isolated efforts. Conclusion: in summary, while the overall framework of SpaceX's recovery protocols may seem straightforward, several nuanced elements are crucial for understanding the significance of this initiative. The focus on data-driven improvements, expert collaboration, rigorous testing, phased implementation, strategic budget allocation, continuous monitoring, and the potential for public-private partnerships highlight a comprehensive and forward-thinking approach to astronaut safety. Recognizing these aspects allows for a deeper appreciation of the complexities and commitments involved in ensuring the safety of astronauts during space missions. Key points for in-depth analysis and discussion. 1. Data-driven assessment phase. The foundational step in SpaceX's recovery protocols is the assessment phase, where historical data and past recovery incidents are meticulously reviewed. This approach is crucial as it leverages lessons learned from previous missions to identify weaknesses and enhance safety measures. By emphasizing a data-driven methodology, SpaceX demonstrates its commitment to continuous improvement and informed decision-making, which is vital in the high-stakes environment of space travel. The use of astronaut feedback and incident reports not only helps in pinpointing specific vulnerabilities but also fosters a culture of transparency and accountability within the organization. This phase sets the tone for the subsequent stages, making it a pivotal point for discussion on how historical data can shape future safety protocols. 2. Innovative development of recovery technologies. The development phase is marked by the creation of new technologies and procedures tailored to meet the demands of modern space missions. This involves designing advanced safety gear and recovery systems that are more resilient to the challenges of space travel. The collaboration with aerospace safety experts highlights a critical aspect of innovation: interdisciplinary teamwork. This phase invites discussion on how innovation in technology directly correlates with astronaut safety. Additionally, it raises questions about the potential impact of emerging technologies, such as artificial intelligence and automation on recovery processes. Analyzing how SpaceX navigates the balance between cutting-edge technology and practical safety applications can provide insights into the future landscape of space travel. 3. Rigorous testing protocols. The testing phase emphasizes the importance of validation through rigorous simulations and live tests under various scenarios. This stage is crucial for ensuring that the new recovery technologies and procedures are reliable and effective before full implementation. By systematically testing each aspect of the recovery protocol, SpaceX can identify any potential shortcomings and make necessary adjustments. This phase underscores the importance of a robust testing culture in aerospace where the margin for error is minimal. Discussions around this phase can encompass the methodologies used in testing, including the role of simulations versus live tests, and the ethical considerations of testing safety protocols in a field where human lives are at stake. 4. Implementation and continuous improvement. The final implementation phase involves not only the rollout of new protocols but also the initiation of training programs for astronauts and recovery teams. This phase is critical for ensuring that all personnel are well acquainted with the new procedures and can respond effectively in emergency situations. Furthermore, the emphasis on continuous monitoring and feedback loops demonstrates SpaceX's commitment to adaptive learning and improvement even after implementation. This aspect invites discussion on the long-term sustainability of safety protocols in aerospace, the challenges of keeping training programs updated with the latest procedures, and how organizations can foster a culture of safety that evolves with technological advancements and operational experiences. These 4 points: data-driven assessment, innovative development, rigorous testing, and comprehensive implementation, represent the core of SpaceX's strategy to enhance astronaut safety through its recovery protocols. Each aspect contributes to a holistic approach to safety in space travel, providing a rich framework for in-depth analysis and discussion on the future of astronaut recovery and safety measures. 1. Apollo 13 Mission 1970. The Apollo 13 mission is one of the most famous examples in spaceflight history of recovery protocols being put to the test. After an oxygen tank exploded on the spacecraft, NASA's ground control team had to quickly develop and implement a series of emergency procedures to ensure the safe return of the astronauts. This included reprogramming the lunar module to serve as a lifeboat and devising ways to conserve resources such as power and oxygen. The incident highlighted the importance of thorough assessment, rapid development of contingency plans, rigorous testing of protocols, and effective training of both astronauts and ground personnel in crisis situations. 2. Challenger disaster 1986. The Space Shuttle Challenger disaster underscored the critical need for robust safety protocols and the importance of using historical data to inform future practice. After the tragic explosion shortly after launch, investigations revealed that there had been multiple warnings about the safety of the O-rings in cold weather conditions. This incident led to a comprehensive reassessment of NASA's safety protocols, including the establishment of a more structured approach to risk management and communication about safety concerns. The implementation of new safety measures and protocols in the aftermath was aimed at preventing such tragedies in the future. Much like SpaceX's current phased approach for astronaut safety. 3. Soyuz 11 1971. The Soyuz 11 mission ended in tragedy when the crew perished during re-entry due to cabin depressurization. This incident prompted significant changes in recovery and safety protocols for future missions. In response, the Soviet space program developed new safety measures, including improved engineering designs for spacecraft and enhanced emergency protocols for crew recovery. The lessons learned from Soyuz 11 led to a re-evaluation of astronaut safety measures and protocols, emphasizing the importance of rigorous testing and training similar to the structured 4-phase approach outlined by SpaceX for its recovery protocols in 2024. In 2024, SpaceX's implementation of enhanced recovery protocols for astronaut safety is a pivotal development in the aerospace industry. The structured approach, encompassing 4 phases and a budget of $3 million, is designed to systematically enhance safety measures throughout the recovery process. Future outlook, predictions for 2025 and beyond. 1. Increased astronaut safety. With the successful implementation of the recovery protocol, SpaceX is likely to see a significant reduction in safety incidents during astronaut recovery operations. This could lead to higher confidence levels among astronauts and mission planners, potentially increasing the frequency of crewed missions. 2. Advancements in recovery technologies. The development phase may yield innovative technologies that could not only benefit SpaceX but also set new industry standards. These advancements could lead to improved safety gear and recovery systems that could be adopted by other aerospace entities. The collaboration with aerospace safety experts may also foster new partnerships and research initiatives. 3. Expanded role of data analytics. The emphasis on data-driven improvements will likely pave the way for more sophisticated data analytics tools in the aerospace sector. This trend could lead to predictive analytics being used to foresee potential safety issues before they arise, enhancing proactive measures in astronaut safety. 4. Influence on regulatory standards. As SpaceX demonstrates effective recovery protocols, regulatory bodies may take notice and consider updating safety regulations and standards for all space operations. This could create a ripple effect throughout the industry, with other companies compelled to enhance their safety protocols to remain competitive. 5. Public-private partnerships. The focus on astronaut safety could encourage more public-private partnerships aimed at research and development in the aerospace sector. These collaborations could lead to shared resources and innovations that benefit both government space agencies and private aerospace companies. 6. Training programs set industry trends. The training programs developed for astronauts and recovery teams may become a benchmark for astronaut training across the industry. Emphasis on rigorous training and simulations could improve overall preparedness for emergency situations, influencing training curricula in other organizations. 7. Increased demand for crew missions. As safety protocols are enhanced and proven effective, there may be a rise in the demand for crewed missions, not only for exploration but also for commercial endeavors. This could lead to a surge in investments and interest in space tourism and other commercial activities related to space travel. 8. Global collaboration in space safety. SpaceX's initiatives could inspire other nations and private companies to adopt similar safety measures, fostering a global standard for astronaut safety in space travel. This collective effort may enhance international collaboration in space missions, focusing on shared safety protocols. 9. Long-term cost savings. While the initial budget allocation might seem substantial, the long-term benefits of enhanced safety measures could lead to significant cost savings for SpaceX. Fewer safety incidents and improved mission success rates could lead to lower insurance premiums and reduced costs associated with emergency recovery efforts. 10. Cultural shift towards safety. Finally, the successful execution of these protocols could instigate a broader cultural shift within the aerospace industry towards prioritizing astronaut safety. This could lead to a more collaborative environment where companies share best practices and lessons learned, ultimately benefiting the entire sector. Conclusion. The implementation of SpaceX's enhanced recovery protocols in 2024 is poised to have far-reaching implications for the future of astronaut safety and space travel. As these protocols unfold through their structured phases, the aerospace industry can anticipate a transformation that prioritizes safety, fosters innovation, and ultimately paves the way for more ambitious missions beyond Earth. The proactive approach taken by SpaceX could set a precedent, encouraging other organizations to follow suit, ultimately contributing to a safer and more sustainable future for space exploration.